All right, I think we are live now. Alicia, do you prefer introducing the guest for us, or do you want me to do it?
Yeah, I can do it.
Then go ahead.
Okay, so good morning, everyone. It's my pleasure to present Marianne Lemoine-Gourmard, who is the research director of the astroparticle groups in SNRs Bordeaux-Gradignan. She's visiting the astroparticle group with one of the fellowships from the Fondation Occident. She's a specialist in the high energy astrophysics universe. So she specialized in supernova remnants and pulsars and, and their nebulae. And she has been working for many years already with the H.E.S.S experiment in Namibia and with the Fermi satellite. So she completed her thesis in the laboratory Le Prince-Ranguet in the École Polytechnique. And after that, she moved to Bordeaux, where she has been working since then. So for her thesis, she was awarded the prize of the École Polytechnique. She also was awarded the Daniel Guigné Prize for the French Physical Society. And now she has been nominated to receive the SNRs Silver Medal in 2026. So please, Marianne, whenever you are ready.
Thank you very much. It is a pleasure to be here. It's unfortunate that we cannot be in person today due to the storm. But well, a special thanks to the Occident Foundation, which made this trip possible. And so my goal today is to show you how gamma ray observations across instruments from GeV to TeV can help us constrain cosmic ray acceleration on supernova remnants, but also in more complex systems, such as star-forming regions. So I go through these different topics. My main expertise is supernova remnant shocks, but I wanted to broaden the topic because we are really in a very interesting phase in gamma ray astronomy, and I wanted to share that with you. I'm working with Fermi since almost 20 years. I'm a member of the Fermi collaboration since 2006. So I'm biased towards GeV astronomy, but I will try to show you some very interesting and very recent results at TeV as well. So since I will try to give you a broad overview of gamma rays, let's see the instruments at gamma ray energies. We've got three types. The most direct is Fermi, because it directly detects the gamma ray on space. It offers, since 2008, its launch, a full coverage of the gamma ray sky from 50 MeV to 100 GeV, even more, but about 100 GeV you're lacking statistics. The inconvenience of Fermi is that its energy and angular resolution is rather poor. It evolves drastically with the energy. The angular resolution is only around 6 degrees at 100 MeV, but improves significantly to being better than 0.1 degree above a few GeV. So this is Fermi. If you want to go at higher energy, you would need a larger instrument, which you can't launch in space. So the best solution is to go in the ground and do it in the indirect way, meaning the gamma ray interacts in the atmosphere, producing a cascade of electron positrons, which would produce a Cherenkov emission that you can detect with Cherenkov telescopes. These Cherenkov telescopes are great. They provide excellent energy and angular resolution, but they can operate only with night sky without clouds, meaning that their duty cycle is very low and you've got small field of view. You've got another solution, which is directly detecting the particles from the shower. For that, you need to go closer to the shower maximum, meaning you need to operate at very high altitude, about 4,000 meters. But these provide full sky, meaning the northern hemisphere or the southern hemisphere, depending where you're located, very high duty cycle, but for angular and energy resolution. So you see the complementarity of the gamma ray instruments we have so far. Fermi provides full-scale coverage at GeV, while ground-based detectors will provide very good angular and energy resolution for Cherenkov telescopes, while the particle detectors will provide very high duty cycle, very large field of view, which is excellent for large sources or for transients. So this coverage and this complementarity is key to disentangle which are the source accelerating cosmic rays in our galaxy. So I will focus in the galaxies since this is my main expertise. We are looking, this is the cosmic ray spectrum. So looking for the cosmic ray accelerators in the galaxy, we are looking to sources able to accelerate particles up to the knee. This feature that we see in the cosmic ray spectrum appearing at 3 × 10⁻15 electron volts. So we're looking for some source efficient enough to accelerate up to this very high energy. And that's not easy because any source that accelerates cosmic rays, the cosmic ray will then escape, traveling in the galaxy, and will lose its information on the acceleration side due to the magnetic field present in the galaxy. While gamma rays produced at the same acceleration side, being neutral, will pinpoint the cosmic ray acceleration. So that's why gamma ray is key in this process. And we've got one favorite candidate since 1934 with Baden's wiki, which is supernova remnants. So it's almost 100 years that we're looking for them, and we didn't find any PV supernova remnants here. So why supernova remnants have been proposed? Because when a massive star explodes, it injects an enormous colossal amount of energy in the interstellar medium. So it produces a shock that will sweep up the interstellar matter, while sweeping up increasing amount of interstellar matter. It will slowly decelerate, producing a reverse shock that will then eat up the ejecta and ultimately compress a potential pulsar nebula. Besides eating the ejecta, these shocks are key in accelerating the particles with what we call diffusive shock acceleration, meaning that the particles will scatter back and forth the shock, generating turbulence that will in turn further accelerate the particles. So there is a magical feedback mechanism there to accelerate the particles. So this diffusive shock acceleration in supernova remnants will produce this polar spectrum that we expect for the cosmic ray spectrum. We can calculate that only 3 supernovae per century with 10% of the kinetic energy of the supernova would be sufficient to maintain the cosmic ray density in the galaxy, but we need them to accelerate up to PV energies. And these PV energies is not that trivial to achieve. So it is determined by 3 different factors. First, the age of the remnant. Of course, you need some time to accelerate your particles up to PV. Then the radiative losses. As the source will age, it will lose energy by radiative losses like synchrotron losses for electrons. And then the third one is the escape. While you accelerate your particle, that sometimes the gyro radius of your particle will become larger than the size of your source and will ultimately escape from the accelerator. So this constraint on the maximum energy achieved by a remnant is not that trivial. There has been a very large number of studies. I won't describe them all. I'm just showing here 2 of them which agree perfectly. So there is one solution proposed by Rebecca Deasing and Damiano Caprioli using semi-analytical modeling. And they show here, you've got one of these this interesting plot showing that the PV particle is here, it's this line. So if you want to reach this PV, you will reach it only during a very, very limited amount of time, just only 200 years maximum. And under very specific conditions, you need either the shock to expand very quickly, like 10,000 kilometers per second for a density of 1 per cubic centimeter. And if you don't have a fast shock, you need your ambient density to be extremely high, above 1 per cubic centimeter. And their conclusion is that you need really specific circumstances, and not all supernova remnants will be able to achieve this Emax. And it's not clear that in the end, 3 supernovae per century will work out. This was the same conclusion by Christopher Riedal in 2020 with Pasquale Blasi, showing that in the end, type 1a are not expected to produce cosmic rays at 2 PeV energies. And only these very specific remnant will be able to accelerate at 2 PeV energies. So this leads me to some interesting targets, which is the core collapse supernova itself. Because massive stars have very strong winds throughout their lifetime, which means that when it collapses, the supernova shock will expand with very high velocity in these dense winds. Since you've got fast shock and very high density, the magnetic field at the shock will be amplified to several hundreds, which is key to accelerate the protons up to PV and then produce gamma ray photons via proton-proton interaction. And indeed, Alexandre Markovits and collaborators have shown that you can reach PV particles for some targets if you take into account the H.E.S.S, the losses, all these different criteria that I've described before. So it opens very good prospects for CTAO, especially for type 2N, which are the most energetic but less frequent. So until then, we haven't detected any, but there is a subclass of supernovae, which very recently became very interesting, which is the superluminous supernovae. So the reason why these supernovae are superluminous is still under debate. It could be due to some interaction with some CSM shells, or to the accretion on a newly formed neutron star or black hole, or to a magnetar wind nebulae that would inject some energy in the system from a millisecond pulse. So since Fermi is covering the full sky, it's easy to try to do some catalog and search for emission from this type of supernovae. There has been a lot of search, which were unsuccessful until the very recent claim by Riedal that the superluminous supernovae 2017 EGN was detected by Fermi. And indeed, so here you see the TS map showing a TS of above 25, so about 5 sigma, during about less than 6 months, and nothing before and nothing after. This detection is now confirmed by the work by Fabio Essero and collaborators, and the work which is under review by the Fermi collaboration is really interesting because it shows and it favors the magnetar model. And under this condition of magnetar model, such superluminous supernovae should be detectable with CTAO. Let's move on to some other shocks and diffusive acceleration. I wanted to mention novae, because in novae, the shock and the variability is happening in almost real time, like real-time laboratory, just in a few weeks or even days sometimes. So a novae is always a binary system containing a white dwarf. And you've got two types of companions, and so two types of novae. Either the companion is a red giant, and we call it a symbiotic nova, or the companion is a solar type star. In this case, we call that a classical nova. Since the launch of Fermi, there has been 182 galactic novae detected mainly at optical. 28 were detected by Fermi. And at TV energies, only one was detected until the results from these summer conferences. So the only one which was detected is HAWC, which is a symbiotic nova detected by H.E.S.S, MAGIC, LST. And at this time, we thought that symbiotic were spatial because you've got a red giant, so a very dense wind and very fast wind. And people thought that classical novae would not be as efficient to accelerate to TV energies. However, we announced at the summer conference, actually my PhD student announced at this summer conference that H.E.S. had some evidence of emission at around 4 sigma level for a classical nova, the classical nova MGAB V207, showing that internal shocks in the wind of the white dwarf might be very efficient as well to accelerate above TV. Since we're detecting TV, it means that we are accelerating above 10 TV in this object, which opens some very interesting prospect for the future at TV energies. So let's move on to some more standard source when we have a talk on supernova remnants, and start with the very famous case of Kepler. So Kepler is a type 1a remnant with CSM interaction. And it took so long to be detected at gamma ray energies. We tried to look for a detection both with Fermi and H.E.S. during a very long time. And in the end, in 2022, both the Fermi and the H.E.S. detection came almost at the same time. It took 152 hours on source to be detected by H.E.S. and Fermi. The issue here, you see the Fermi H.E.S. map, is that the angular resolution from Fermi, but also with H.E.S., because it's faint, doesn't allow us to constrain the emission region. The good thing with Kepler is that we've got lots of multi-wavelength data that can allow to constrain what we're seeing with at gamma energies. We know that it is very heterogeneous. There is strong interaction with CSM, with dense CSM and lower shock traced by this H-alpha emission in the northwest, whereas in the southeast, we know that there is a very fast shock and this strong electron synchrotron emission that you can see in blue. So our idea was that proton-proton interaction would better take place in this region, whereas electron acceleration and emission via synchrotron and inverse Compton scattering would better arise from this region. So we've done a modeling of both the Fermi and H.E.S. data in our paper, and you can see here what our modeling in two different scenarios. So we fixed most of the parameters from the literature, from Chandra data, Hubble data. So we have only the magnetic field, the energy injected in electrons and protons, and the spectral index, which are free. And you see that in both scenarios, the Fermi emission has to come from proton-proton interaction from the northwest region, whereas the emission detected by H.E.S. can come from either from proton-proton interaction or from inverse Compton scattering in the southeast. The very good point is that CTAO, with its increased sensitivity and angular resolution, will be able to constrain the location of the gamma ray emission and therefore constrain the magnetic field at the shock, and therefore constraining diffusive shock acceleration at the shock. So you see the SED of Tycho, which is extremely similar to Kepler, and in both cases, the proton energy is only 4% of the kinetic energy of the supernova, meaning that we are very low with respect to the 10% that we would need to maintain the cosmic ray flux in the galaxy. Let's move on to SN1006. It's so famous that I cannot resist in showing it. It was the first one for which X-ray synchrotron emission could prove that very high energy electrons were indeed accelerated in these two rims. Since then, with improved observation at X-ray from Chandra and XMM, we've seen these very thin X-ray filaments showing that there is very high B fields in these two rings. Then it was detected by H.E.S.S with a very good correlation with the X-ray emission. And we know that overall the remnant is evolving in a very low ambient medium, which doesn't favor at all proton-proton interaction. So if there are proton accelerated, we cannot trace them just because proton-proton interaction is not efficient, because the density is too low. But Marco Micheli and collaborators published in 2014 the presence of an atomic cloud in the southwest part of the remnant, where efficient acceleration is taking place. So we've looked at the Fermi data. You see here the Fermi image showing both the detection of both the northeast and southwest rim, though without the nice resolution from H.E.S.S and from X-ray, of course. Here we have an angular resolution on average of 0.2 degrees, so we need to rescale it. But analyzing simultaneously the northeast, the southwest, trying to get a spectrum from these two sides with Fermi, getting data from H.E.S.S for these two rims, and from the X-ray and the radio, we can see that the spectrum, at least from Fermi, is different in the northeast and the southwest. It's much softer in the southwest, and our modeling shows that we can completely reproduce the whole results just by scaling the density. If you rescale the density by a factor of 10 in the southwest due to this atomic cloud, which is being still very low, less than 1 per cubic centimeter, you can reproduce fully the gamma ray data, the X-ray data in the northeast and the southwest. So it could be that protons are indeed accelerated in all these remnants, but just that we don't see them because the density is not high enough. It's high enough only here in the southwest. So let's put all these results into one plot. You see the Fermi and H.E.S.S data from the shell-type remnants RX13, VERITAS Junior, SN1006, RCW86, in comparison to a middle-aged remnant like W44. You see that they are all extremely similar, favoring a similar physical scenario, favoring which is very hard in the Fermi band. So it favors an inverse Compton scenario with the same seed photons being for all of them mainly the CMB photons. But as I've just said, protons might play an important role in some subregions, and they can be only detected in some subregions where the density is high enough. Even when you don't have detection, you can constrain what is happening in a source. So we've worked with François Brun on the H.E.S.S Galactic Plane Survey, which released flux upper limit maps. Everything is public, so you can freely access them. And we looked at the 4FGLDR4 catalog, which also, since NASA requires it, we've released the SED, the spectral point, the TS for all the sources in the 4FGL catalog. So if you look at sources, Fermi sources, in the galactic plane covered by H.E.S.S, outside region with 5 sigma detection, which we've masked with a very large mask to take into account the PSF, then we've got 418 sources, and 13 of them are severely constrained by the S upper limits from this flux upper limit max. So it's public. You can play this game. It's easy. You see here the Fermi SED from the 4FGFDF4 catalog. This is the S upper limit from this source, which is quite interesting because the Fermi position is right on top to a supernova remnant, to a shell type remnant. So this is quite interesting because you see this Fermi spectrum and the S, so it seems to favor something very, very peaky, such as inverse Compton peak. But we know that this shell type is interacting with the molecular cloud there. There is some major emission. So it deserves all these 13 that we've published there would deserve some spatial analysis and another look at TV especially. So let's move on. We've seen with this plot here that the young shell type remnants are very different to middle-aged remnants. So there must be something, some kind of evolution when you go from young age to middle age. What's happening? So we've worked with Roberta Giuffrida from Palermo to see how the evolution is happening. And one very nice case is the remnant papacy. So papacy is old enough to be in this kind of transition. It's about 4,000 years. And we know that it is very, very asymmetric. It is interacting with very dense clouds in this region, whereas the other side is evolving, the shock is evolving almost freely. And the very good thing is that we've got very good multi-wavelength coverage, but also it's extremely bright with Fermi. We detected it only with 4 years of observation. You see that the spectrum is very precise. This was the first one published in 2012. So here is what Roberta has done, working on the spectrum above 300 MeV. You see here the density of the medium, which is extremely high on this side of the remnant, very low in the opposite. And you see here the X-ray image showing that it's very bright. It's a thermal X-ray emission that you see here, much fainter in the other side. So if you look at the Fermi spectrum from this side, you see something very curved, like what we see with W44, which resembles the reacceleration of the cosmic ray C, whereas in this side, it's a pure Paolo, which is very similar to what you would expect from diffusive shock acceleration. So this shows how the environment is crucial. This region will evolve much faster interacting with the molecular cloud, whereas this region is still in a set of Taylor space with still accelerating particles efficiently. This papacy is also quite interesting because it tackles another extremely interesting topic, the topic of escaping protons. So as I said, when you accelerate your particles at the shock, at some time, their gyro radius will become so large that it will ultimately escape from the remnant. So escaping, the proton can travel in the ISM and potentially interact with the nearby clouds. And interacting with the molecular cloud, it will produce gamma rays via proton-proton interaction. So nearby cloud can be very bright at gamma rays just due to the escape of protons. And that's what you see here in this diagram, showing that the gamma ray flux from the supernova remnant will lose energy because you lose particles, while the gamma ray emission over time from the cloud is shifting also to lower energy, but it peaks at 100 TeV earlier times. So that's what we see. That's what we may see for PAPIS-A. You see PAPIS-A here. And we've got two gamma ray sources, north and south of it, which coincide perfectly with overdensity. These two sources have hard spectra, which is predicted if indeed it is high energy protons that escape, you should see something quite hard, which you see in this diagram. Trying to consider a sphere centered on PAPIS-A, we calculated the energy needed on cosmic ray to reproduce the flux that we're seeing. And it's about 10 to the 5th here. So everything is consistent with supernova remnant being accelerating cosmic ray at the shock and then released in the interstellar matter. This passively illuminated clouds is a topic that became very famous, especially at this summer conference, at this ICRC. It was in many different presentations. So I just want to highlight some work that has been done by Alison Mitchell and Sylvia Celli. You might all have heard about the LHAASO detection of a lot of sources which reach PV energy. Some of them are unidentified, but could be due to this escape from protons from a remnant, which illuminates clouds. And even though you're not detecting PV emission at the remnant, there could have been a PeVatron before, just that the PV protons have escaped. So this game is to pair a remnant with some molecular clouds. So of course, the molecular cloud doesn't have to be too far away, but then the cosmic rays will never reach the cloud. So the physical separation has to be relatively low. And then they model the escape, taking into account this diffusion coefficient at 1 GeV, and they try to see if the gamma ray emission that they produce at the cloud is consistent with the LHAASO spectra. This is the case, especially the case for one source, this LHAASO source G1857, where you see here the spectrum from LHAASO. It also coincides with the H.E.S.S unidentified source, and you see the spectrum derived by Alison Mitchell and Sylvia Celli on this source, which reproduce perfectly the whole system. So in this case, if it is true, this molecular cloud on which the LHAASO source is coincident would be illuminated by the nearby remnant G36.6 minus 0.7. There was also a presentation at this ICRC with this source, which is a very complex system. So there is a LHAASO source here, LHAASO J1929, which sits right on top of a molecular cloud. It became very famous because it is coincident with, you see these black lines, these are the different level of confidence from the track-like event from IceCube. So there is a neutrino event which coincides slightly with this LHAASO source. And again, if you play this game of a remnant which illuminates the cloud, you can reproduce perfectly the LHAASO source. And this would mean that the remnant would have been a PeVatron in the past. This game can also be done even though you don't have a remnant. And this was done by Alison Mitchell for the LHAASO source J2108. Here we know that the LHAASO source is right on top of a molecular cloud. So you fix the cloud properties and you see what would be the condition, the parameters for a remnant to reproduce the LHAASO source. So it's not LHAASO detected the source, and we've got also some constraints from HAWC, from VERITAS, from LST. And you see that in this modeling, what she would need is that she would need a rather young remnant near to the cloud. And looking at the archive, there is no such remnant known. But with ASCAP and MERCAT, it might be that in the near future, a remnant would be detected in this region. So let's move on with Fermi catalogs. We, as NASA requires, we've published several catalogs. The first one was released in 2017 with 46 extended sources. A second, the year after, at high latitude with 19 others. And then last year, we published the 22 other extended sources. In this catalog that I've developed, there was one very interesting target, the remnant G150. This remnant was reported just a few years before we published our own catalog. You see here the remnant at radio. It's 2.5 degrees, so it's very large for to be observed with the Cherenkov telescope. If we do the Fermi analysis, you see our green circle, which coincides perfectly with the radio side. That analyzing the source, we detected an excellent source plus a point source there. And this point source, take care here, it's Radec, here it's LB. It coincides perfectly with these emissions, which have a different spectral index, which would be more consistent with the pulsar wave nebulae rather than the other would be more consistent with a remnant. So we looked at the Fermi data alone, and if you look at the SCD, it matched perfectly with the SCD from Villa Junior and Eric 2013. So at this time, with Justine, we proposed, if you look at the luminosity for a nearby source or a faraway source, since the distance for this remnant is not well constrained, we proposed that it was a young, well, dynamically young shell type, which would be nearby without any interaction, and that the point source would be a potential putative pulsar. That was our proposal. But since then, LHAASO came in the game, showing that they have a very large source at low energy, which is consistent with the remnant, but at high energy, they detect much compact close to the point source that was detected with Fermi. So I was very happy. I said, oh, great. They detect the remnant and they detect a pulsar wave nebulae, which would be associated to our putative pulsar. But the paper, which was released by LHAASO, said, no, we've detected a PeVatron. We are detecting molecular clouds that escape and interact here in this molecular cloud. So here it's clear that radio or X-ray observation would be key to disentangle if there is a pulsar wave nebulae there or a putative pulsar. To disentangle between our suggestion or this suggestion of a PeVatron source with a remnant. But this source, G150, is not alone. Now we've got several sources of the same kind, which lies outside the plane, which are relatively large, which are all very bright at gamma ray energy and very dim at radio energy, showing that gamma rays can be key in detecting some remnants to solve the puzzle of the missing remnant in the galaxy. So you see that this catalog is increasing, and all of them, they share the same very hard gamma ray spectra and low luminosity for the synchrotron. So let's move on to middle-age remnants. This was already published 10 years ago. You see these gamma ray spectra from W44 and IC443, which are characteristic of what you would expect for proton-proton interaction in this dense medium. So IC443 since then has covered a lot of attention because it's very bright and it's very interesting. It is evolving in a very complex medium. It is evolving interacting with the dense molecular clouds that you can see here in the south and west. There is lower density in the northeast, so it's very inhomogeneous. And you see the beautiful VERITAS image and the Fermi Count map, which agree perfectly together, but also with the tracer of CO map. So that's IC443 that you can see here. Now I'd like to show you this because of this small filament and emission here. So actually, IC443 is not alone. It is close to a remnant that you can see here with Rosita, which is called G189.6. So Rosita was not first. It was first discovered by Rosat in 1994. But we didn't know that it was a remnant since the new observation by Rosita, which proved the supernova remnant nature of this nearby source. So we have analyzed the Fermi data, and what we've detected is that the emission is separated in two components with Fermi. We've got one component which overlaps with the full remnant, which is very large, and another component very peaky here toward this filament, which trace the interaction with an H2 cloud. So this interaction with an H2 cloud, with the same H2 cloud with which IC443 is interacting, proves that IC443 and SNR G189 are interacting with the same molecular cloud, and then prove that they are at similar distances. So we've submitted this paper with Miltiades recently, and this new Fermi data analysis showed that these two remnants could come from the same binary system, and that would be the first time. And you see here the spectra derived with Fermi, which really prove that there is really two components, one from the remnant and one from this PQ region where the interaction is coming from. So there is really something taking place with this H2 region, which cannot come only from IC443, which has to come from G189. These spectral breaks are key to pinpoint cosmic ray accelerators. So that's something that we've tried, is looking for spectral breaks at low energy with Fermi. We've seen 56 sources with spectral breaks with Fermi, and among these 56 sources, supernova remnant is the dominant class. So here are the spectra rescaled for this certain source. There is only one outlier, which is gamma Cygni 2 due to the potential contamination from the bright pulsar. So for gamma Cygni, you would need to work in the off pulse of the pulsar, which you cannot do in a catalog. But you see that they all are in very good agreement with what you would expect from proton-proton interaction. So all of them are accelerating or re-accelerating protons. But there is something interesting which I would like to cover in just 2 slides. These are the class of sources that we have analyzed. Of course, a very large number in the galactic plane, since we work in the plane, are unidentified in Fermi. But among the identified class, 2 class pop up. The one that we were expecting to see, remnants, and another one, which is binaries. So despite that small fraction, we only analyzed a couple. Binaries might contribute and might play a role in the acceleration of cosmic rays. And I'm just showing that it's very far from my main expertise, but I think it's becoming something quite important in cosmic ray physics in the galaxy. So binaries, we've got a real zoom. It could be, can have binaries with an accretion disk and a jet. You can have binaries containing non-accreting pulsars. You can have binaries with massive star binaries like Eta Carinae. And in all of them, you've got shocks and non-thermal emission. And all of them have timescales that are relatively short because they are compact. So I wanted to show this with HESS because thanks to HAWC, to the full sky coverage of HAWC, this source was detected. And then it was long observed with HESS, showing this bright emission coincident with the X-ray emission. And due to the energy-dependent morphology that we see with HESS, we can clearly favor an electron acceleration, so no protons here, up to at least 200 TeV, happening 25 parsecs from the black hole system. So that's for HESS, but it could have been a complete outlier. It turns out that there are others. Since then, HAWC detected V4641 SGR. We had only a couple of data with HESS, so we reobserved the source, and it turned out that there is a huge emission. It's 100 parsec long if you assume the distance of this source at 6.2 kiloparsec. And V4641 SGR is not at the center of this thing. And there is no thing like high density medium in this region. So the way to explain it is quite puzzling. We don't really know the origin of this gamma ray source. And so with Fermi, we've looked at the Fermi data, there's nothing. So it means that you've got a very hard spectrum. And it requires a very low B field, much lower than what we see with SF433. So this is really puzzling. And the puzzle doesn't stop there. No, we've got LHAASO. And LHAASO published this spectrum for V4641 SGR going to PV energies. So it means that you would need, if you believe them, protons up to 10 PV. And this is SF433. They claim that the inverse Compton would be suppressed due to the Clinician effect, and that they need some hadronic components to reproduce the spectrum that they have at the highest energies. So it's becoming quite interesting, and I hope that with CTAO and AS3, we will be soon able to constrain these nice results. And I'm to the end of my talk with one last topic. We've seen that actually the more we detect remnants, the more we see that the PV protons is very hard to achieve. And this 10% of the energy, of the kinetic energy of the supernova is it's not clear that it is happening. At least we don't see it for Kepler and Tycho. It may be the case for SN1006, but only in the rings. So we have to think a bit more. Actually, massive stars are produced at the collapse of giant molecular clocks. And usually they form compact groups of massive stars. So you don't really expect an isolated remnant something in the plane. You should have some groups of all types of stars which would remain linked during their life. And if you think about it, then this would create super bubbles with stellar winds and supernova explosion, which would be filled with turbulent plasma shocks. And this turbulence might be might be bringing very favorable conditions to accelerate further the cosmic rays than in individual remnants. And that's a sketch of the best candidates that was proposed very recently by Giovanni Molino and Thibaut Vieux of a bonded group of stars, like a massive star cluster, which would have a supernovae occurring close to some group of Wolf-Rayet, which would have the winds with some turbulence, which would further accelerate the cosmic rays and then producing a wind termination shock. So in their paper, they've shown that in this condition, this favorable condition, you could even achieve 10 PeV for a supernova remnant embedded in a wind termination shock. Fair enough, but then we've got to prove it at gamma rays. And that will be one of my last slides. It's the topic of Western 1. It turns out that Western 1 is the most massive non-young stellar cluster in the Milky Way, and it's relatively young. And we know that there is an extreme magnetar, meaning that there is at least one supernova that occurred in the cluster. It was detected by H.E.S.S with a ring-like, shale-like structure, which was proposed to be that there is electron acceleration happening at the cluster wind termination shock, and we would be detecting with H.E.S.S the inverse Compton emission from these electrons. Okay, that's the H.E.S.S contours, and with H.E.S.S, since we covered between 2 and -2 degrees with the H.E.S galactic plane survey, we didn't have exposure far outside the plane. But we were seeing some here that you can see here, and we were wondering what is that? So we analyzed the Fermi data between 3 GeV and 3 TeV to cover the low energy with of H.E.S.S. And this is what we detected with Fermi. We detect a very large source going up to -3 degrees from the plane. It's a very extended emission. At the 4 kiloparsec from Western 1, it's 100 parsec. And it is a very complex study that we've done, actually. Here it's the Gaussian that connects perfectly to Western 1 with some emission detected inside Western 1. But to explain you what we had to do, Fermi is detecting point source. So you have here these blue cyan stars, the point source that were detected in the catalog with Fermi. And we had to iterate to find the best morphology for this source, which turns out to be the northern part of the Western 1 shell plus a Gaussian, removing all these point sources, which are all just one single component. So there is a huge improvement in fit quality by just taking into account the H.E.S.S emission for a Western 1 plus a Gaussian. So now, what is this Gaussian? So we proposed a scenario in the paper that was recently accepted by Nature.com, which should be published very soon. So you see here the cluster wind termination shock, which will accelerate electrons, but also protons. These high energy electrons will lose energy quickly, producing the TeV emission that we see here in green. And the low energy electrons will be transported along the outflow and produce the GeV outflow that we're detecting with this 100 parsec long. I don't want to go into too many details, but modeling that, we require an energy density of about 1 to 10 electron volt per cubic centimeter. With diffusive shock acceleration, we predict an electron UP to be larger than UP. So it might very well be that the outflow is loaded with cosmic rays and potentially driven by these cosmic rays. So that's quite interesting because it goes in the light with other very interesting sources like the Cygnus region, which is in the northern hemisphere, for which as well there is this spectral break at low energy showing that there are protons accelerated. It was detected by HAWC and then announced by LHAASO at PeV energies. So there again, here's this star forming region accelerating up to PeV energies. And it is not an isolated case. We've got Western 1, we've got the Cygnus, and we've got others. We are currently in the process of finalizing a Fermi-LAT catalog on bright clusters. And I'm showing you the one that were already announced with that 20 sources detected significant. So I'm going to my conclusion. It's really a nice time with lots of surprise. We've got these binaries, we've got the variability, we've got hadronicity, we're detecting the superluminous supernovae, the novae, we're detecting some binaries up to PeV. In all of that, the environment is key. It's key for the evolution of the acceleration, but also to detect the protons via proton-proton interaction. We've got this new population of radio-dim remnants showing that gamma ray energies might be key for some subclass of remnants. And I hope you've seen that this collective effect would be important and that stellar clusters might contribute efficiently to cosmic ray acceleration. So it's clear now that the multi-wavelength synergy, in particular with radio and X-ray instruments, but also with neutrino, is crucial to really disentangle and constrain our gamma ray observation with the very nice results that we will get very soon with CETAO especially. And I will stop there.
Thank you very much for this nice talk. Let's clap virtually to thank the speaker first. All right. So it's time for questions. So if you have any questions, please raise your hand and then we will go through the chat in order. Okay, I think we have one question from Alicia. So whenever you're ready, please go ahead.
Yeah, hi. Thank you for the very nice review. So I was wondering, so can you remind us how does Fermi see the Cygnus bubble? Because the LHAASO emission is very extended, no? Is the Fermi one that you see also that extended, or is it more focused on some region?
Yeah, no, it is much more focused. It's like 4 degrees across. So with Fermi. So, well, I was wondering with LHAASO, what is really due to the real extent? It's not really measured. So I'm wondering what is due to the PSF and what is real, and what is due to confusion of sources. But the Cygnus cocoon for Fermi is like 4 degrees across.
Okay, thank you.
All right, more questions then. I actually do have a question. I don't know if you have any news on what is the situation with Fermi, if it will be get extended, and if the mission will continue with all of the issues that we have been having so far.
We don't have really a lot of news. We have to pass every 3 years over the senior review panel. And this senior review has told NASA that Fermi has to be extended by 3 more years. So that's science. And in science, they want Fermi to continue. That's a good point. Now comes politics and budget. The proposed budget proposed that Fermi has 0, meaning that Fermi would be desorbited. But we don't know what is the reevaluation of the budget, know that the shutdown is over. But we should know very soon. So we're just crossing the fingers, because really Fermi is key in this process to constrain this break, but also to constrain the spectral shape, so the spectral injection. The TV particle the TV instruments are key to constrain the maximum energy, but without Fermi, we'll have some hard time to constrain the injection. And it is also key for transients, which I haven't mentioned a lot so far, apart from novae. But for instance, H.E.S.S relies a lot on Fermi triggers for novae. Each time a nova is detected by the LAT, HESS is observing it. I guess it's the same for other TV telescopes. It would be really an issue if we don't have Fermi.
Indeed, we all hope it will be continue giving us these very nice scientific results. Okay, so do we have any more questions from the audience? We have time for one more. If not, I think we can thank the speaker again. And hopefully next time we will be able to welcome you in person. But at least for today, we are happy that you were able to give us this talk. Okay, so before saying goodbye, if you are a student and want your attendance to be counted, you should have been counted by Mayalen by now. If not, do it now, then we will keep note of your attendance. Thank you, everyone. Goodbye.
Thank you. Bye-bye.